Hello everyone. Thank you for coming. So today I'll be talking about a project that I started along with a number of students and collaborators in Munich. And it's about formalizing different results from the theory of combinatorial optimization. Before I start that, I would like to firstly tell you what is combinatorial optimization. So as the Wikipedia definition says, it's a subfield of mathematical optimization that consists of finding an optimal object from a finite set of objects. And the interesting part here is that it's real concern with only sets of objects that have a mathematical structure that allow you to come up with an efficient way of searching through that set of objects. It's not just like brute force methods are not really interesting in combinatorial optimization. So problems that belong to combinatorial optimization that have such a nice mathematical structure that allow you to have efficient algorithms include shortest paths, spanning trees, matchings, and flows, and traveling salesman, or set covers and EM programming and problems on Markov decision processes. There are so many of them. Okay, so that is combinatorial optimization. So the goal of this project, it's not like a properly planned project. It was an organic one, but it evolved into aiming at building a formal library of graduate and research level results in combinatorial optimization. And the focus was, as I stated earlier, on problems for which there are polynomial-time algorithms, or for which there is that have some sort of interesting mathematical structure that allows you to do something better than brute force. So the goal was to have a formal library in Isabelle that corresponds to results in a book like Schreifer's book or Kota and Fiegen's book, both of which are standard books in combinatorial optimization. And also we veered a little bit more than that and worked a little on research level results that wouldn't necessarily be in such a book. So these are usually master's levels book or first year PhD books, and we also did some results that are just research. I don't know whether it's a problem with my machine or with wires or what. Anyway, so I will focus on some results related to graph matchings. So matching, which is one specific problem of combinatorial optimization, and I will try while talking to demonstrate what types of objects you need to model in formalizing such results, the types of reasoning you need to formalize, and also the types of contributions that I think formalization might bring to those areas other than just building formal libraries. So I must firstly start by saying that this is not the first type of work that tackles combinatorial optimization from a formal formalization perspective. There's a lot of work already on shortest paths and maximum flows and approximation algorithms and linear programming and spanning trees. So this is one of the earlier areas that were formalized, not the earliest, but earlier. There are results from the early 2000s in Mizar. So this is not the first project, but this is the first project that actually works on matching. And also, I think we reached relatively deeper algorithms than what was formalized before, and deeper results. So what is matching? So you have an undirected graph. A matching is a subset of edges of that graph such that no two edges are incident on the same vertex in that subset. Okay? A maximum cardinality matching is simply the largest such subset of edges of a graph that is a matching, right? Does that make sense? Okay. So here, for example, in our example, these green edges are matching because none of the edges are there are no two edges that are incident on the same vertex, and it's a maximum cardinality matching because you cannot add any other edge or you cannot come up with any other set subset of the edges that is bigger than that. The first, so I will talk about three results, three pieces of work related to matching here. The first one is Edmonds blossom shifting algorithm, and this is an algorithm to compute maximum cardinality matchings for general graphs, general undirected graphs. So they don't have to be bipartite, they don't have to be any undirected graph. This algorithm can compute in polynomial time a maximum cardinality matching. And why is that interesting? Why is that? So maybe just say one specific thing. We focused specifically on formalizing the result, the correctness proof of this algorithm that's in some optimization book called LEDA by Kurt Milhor and Stefan Neher. And this work I did it in collaboration with Tobias Nilko and Kurt Milhor. So why focus on Edmonds-Blossom algorithm? Well, historically, Edmonds-Blossom algorithm is very important in the theory of computing. It is this algorithm, while coming up with this algorithm, Jack Edmonds inspired him, apparently, to identify the notion of efficient computation with polynomial running time computation. So it is the first paper that has that notion, so it's historically important. But also from a verification perspective and from a formalization perspective, it is the second most complicated algorithm in this data book, and Kurt Milhor tried to do it to formalize its correctness proof in 2010 or so, and could not, and estimated that it would be a many person-year project. And
was he using Isabelle? Or?
Sorry? Yeah, he was using Isabelle. Yeah. And before, I will just give you a bit of a spoiler. So indeed, in order for us to finish this proof, we had to come up with to finish formalizing this proof, we had to come up with new mathematical insights. We couldn't formalize the standard proofs. So let me go a little more into the algorithm, just to give you a sense of what sort of concepts you need to model in a theorem prover if you want to reason about these algorithms. So the algorithm is, in general, this algorithm has the same path, follows a similar pattern of all other optimization algorithms. So you start with the algorithm takes the graph as an input and the current matching, a current solution, as another input. And what it does is it tries to find a way to improve that solution. So here for example, in the case of matching, we can improve our current matching by finding a so-called augmenting path, and I'll tell you in a second what that is. And if you find that augmenting path, then you recursively call yourself again, but with the matching improved with that augmenting path. And I'll also explain how is the matching improved in a second. So what is an augmenting path? It is a sequence of edges such that the first and the last vertices are not in the matching, and such that every two consecutive edges alternate in membership in the matching. So one edge is in the matching, in the current matching, one edge is not in the current matching. And I'll show you an example. So for instance, if we have this graph here, those two green edges are matching. They're not a maximum cardinality matching, but they are matching. And this sequence of red edges is an augmenting path. Why? Because U1 and U6 are not in the matching, as you can see, and every edge in the like every two consecutive edges of those red edges alternate in terms of membership in the matching. We can use the augmenting path to make the matching bigger by taking the symmetric difference between both sets of edges. So the symmetric difference of two sets is just the set of elements that are exclusively in one of the two sets. So here, the symmetric difference between this red path and that small matching is this edge and that edge and that edge, because those are only in the path but not both in the path and the matching. Okay? And as you can see, by taking the symmetric difference, we make the matching bigger. And the algorithm continues trying to make the matching bigger by finding such augmenting paths. So why is this correct? The correctness or let me be more precise. How do we know that if there are no further augmenting paths, that this matching is maximum in cardinality, right? So this results follows from a theorem from the 1950s by Berge, and it says a matching has a maximum cardinality if and only if it has no augmenting paths. Right? So proving this theorem is already was already a problem for the first trials, formalize that proof. And let me take you through the proof a little and show you how we managed to formalize and prove it correct. So the first direction of the theorem, in the first direction, you need to show that if you have an augmenting path and the matching, you can make the matching bigger by taking the symmetric difference. And that's easy. That's very straightforward. There's nothing to think about there. Very easy to formalize. The other direction is the hard one, which is that if there isn't an augmenting path, how do you know that this matching is maximum? So I won't be able to go through the proof because the proof is long, but I will just tell you about one specific proof that one specific step of the proof that made its formalization difficult. And that step is the following: if you're given any two matchings for a graph, the symmetric difference of those two matchings, right? So we're talking about if you have two matchings, their symmetric difference will have connected components that look as one of three things. So every connected component in this symmetric difference between the two matchings is either a singleton vertex, an alternating path, or an even alternating cycle. An alternating path, if you remember, a path whose edges alternate in terms of membership of one of the matchings. So this is a complex construction, and we basically came up with a proof that just avoids this lemma. So it's a much shorter proof. That's one thing that came out of this formulation. Just we could avoid this. We were able to avoid this step, and this step is in the standard proof on Wikipedia and everywhere. If you look at it graphically or informally, it's relatively easy to see why this would hold. But if you try to formalize that, then it becomes really complicated. So we had to avoid it. A second part of this algorithm has to do with how do we find how do we find augmenting paths, right? So intuitively or naively, one would try to find an augmenting path by either by modifying breadth first search or depth first search, and having them look for paths that alternate in terms of membership of the matching. But I won't be able to tell you why, but I'm more than happy to answer the question if you're interested. But both breadth first search and depth first search do not work because they will give you augmenting paths that have odd cycles. If you are interested in this, just try yourself augmenting a matching with an augmenting path that has an odd cycle, and you will see it doesn't work. So the end result here is that we cannot have augmenting paths that have odd cycles. How can we avoid that if breadth first search and depth first search do not work? Well, the way to avoid that is by simply removing odd cycles. So you modify the algorithm to make it search for either augmenting paths or odd cycles. If it finds an odd cycle, it just removes it by contracting into one vertex like this. And then you start to search again. And this was the main insight this is the main insight of Edmonds Blossom algorithm, that if you do that, you still maintain polynomial time. You still can do it in polynomial time. So you search for an augmenting path or a cycle, an odd cycle, and if you find an odd cycle, you contract it into one vertex and then you restart again. And of course, that depends on proving that a graph has an augmenting path if and only if the contracted graph also has an augmenting path. So otherwise, this step is not sound, right? Because you might be missing some paths, some augmenting paths by contracting these odd cycles.
Mohammad?
Yeah.
So Mohammad now was looking for the witness producing algorithm.
Yeah.
Did you do that?
I will talk about the certificate in a second, in 2 slides. Yeah. Yeah. What were we saying? So how do we prove that by contracting these odd cycles we don't miss any augmenting paths? There are 2 directions in that proof, of course. Like an augmenting path in this graph is an augmenting path here, and if you have one here, then there is one there. So you have to do 2 constructions, and in a nutshell, those 2 constructions are just proving them it has many cases, and they're not tedious, just thousands of cases like some proofs some other kinds of combinatorial proofs, but these are cases that you really need to think about each one of them separately and sit with a pen and paper and understand them. And one thing that was in Milhorn's later proof is that he thought that he could just circumvent, like he could just do one of the two directions and not the other. Yet he can, and he thought that his correctness proof doesn't need the other direction. And one outcome of this formalization is that it actually, his lemma that he thought doesn't need this one of the two directions in this blossom contraction proof is, well, it's not incorrect technically, but in order for you to prove it, the only way to prove it is by proving what he was hoping to circumvent. So he didn't. So we have to prove both directions, and he was surprised to know that. And this is also an outcome of that formalization. And from a formalization perspective, let me just quickly say, like these proofs showed that theorem provers can be significantly improved if we have symmetry breaking there, because there are many symmetric cases, and you have to really come up with dilemmas on your own that remove the symmetries, or otherwise you'll have to repeat proofs. So it would be nice if we have an automated way that's like what's done in stat solving or in other areas of automated reasoning. The last thing is how do we actually find an augmenting path or a cycle? And I will not be able to explain that to you in details, but I just want to show you one thing, again, with the hope that you can capture what kind of things do we need to model when you reason about these algorithms. So I don't want you to read this algorithm because it's not going to be useful, but all I want you to see is that we have a while loop with just two branches, if and else, and the while condition, but the control flow, but this short while loop actually hides a very complicated control flow that I think cannot be done, cannot be, no human can reason about it manually without making some mistakes. So how did we model this while loop? The modeling itself is not a big problem, we just used recursion. I know a lot of people are using, came up with while combinations and other ways to model while loops, but in here, when you're proving an algorithm correct at a mathematical level, it doesn't matter if you just use normal recursion. And program states are modeled using Isabelle records. So that's not a big deal. How can you prove such a loop correct? As I'm saying, this is not doable manually because you will always miss something because of this very complicated control flow. But let me just give you a glimpse of how do you prove such a loop correct. So you prove firstly partial correctness, namely if the loop returns to you something, then that thing is sound, right? In this case, the loop returns to you two paths that you can use to either construct an augmenting path or an odd cycle. And those two paths have to have many properties in order for them to be able to help you construct an augmenting path or an odd cycle. And of course, you have to come up with these properties, bearing in mind that they have to imply what you finally hope for from this loop. And the total correctness, which is the other direction, and here we come to Shankar's question. We construct, we prove that if the while loop terminates without finding anything, then you can use the variables in the loop to construct a certificate that shows that there isn't an augmenting path. And in Kurt Melhorn's earlier approach, he just constructed that certificate and checked it manually, with a checker. But in this formalization, we show that you can always construct it if the loop tells you there are no augmenting paths or odd cycles. To prove a loop like that correct, you need so-called loop invariants, and these are just properties of the variables that are in the loop that have to hold. Here, we needed 18 loop invariants, and I'm talking here about invariants that are mathematically meaningful, not invariants about implementation details. And in his initial proof, Kurt thought that he can do it just with 11 invariants because he thought that he can, as I said, again, circumvent one of the two directions of the Blossom contraction theorem.
How do you model an open-ended loop? Do you have a You just give it some fuel.
Well, we have here to prove terminations. It cannot be an open.
Right. So
how do you model an open-ended loop? Just as a recursive function. A recursive function that takes a program state as its argument and does some things, and then gives that program state to the next call, and then you have to show some measure.
That's what I'm asking.
Yeah.
What's the measure that you show?
The measure here is the set of unexamined edges. So this is for the invariance, and yeah, sorry, my train of thought is a bit. I lost a little. So we showed that we had like 11 of those invariants, but we needed extra 7, and these have to do with the step that he thought he can circumvent, and we came up with a much shorter proof for Bear's length. And because of this formalization, I asked him to give me this quote so I can use it in these talks and other things to just make sure that I'm not making up stuff. So he really did, he says he couldn't understand this step that he thought he could circumvent without the formalization. Because as I'm saying, we're keeping, like here this is not about just a quantity of cases that you just need a machine to go through them one by one and they're all trivial. No, here it's about you want to do a manual analysis, but you cannot do it. And you have to use a theorem prover to help you keep track of the interconnections of all the different parts of the algorithm, for example, that are interacting. So, I mean, I have to still finish at 40, right?
Well, 45.
Okay.
But then that's already the questions.
Okay. No, I mean, well, 35 versus 40 then.
Yeah.
So another thing I wanted to discuss with you, and another matching-related result out of this during this work that I want to discuss with you is online bipartite matching. And I won't spend much of the time here. I want to just give you a glimpse of, again, it's a different kind of things that you need to model. So this is an online algorithm. What does that mean? It's an algorithm whose input arrives online. And as the input is arriving, you have to compute the output before the next part of the input arrives. So the input arrives in pieces. When a piece of the input comes, you have to compute you have to decide whether you will use it in the output or no before the next piece of the input. So let me just show you here in this. So this is so we're talking here about an algorithm for online bipartite matching. So you have two parties in the graph. One of them is offline and the other one is online. And what I mean by online here, that means that every vertex arrives along with its incident edges online, right? So here, for example, U1 arrived along with its incident edges, and then you have to make a decision whether you want to use these or include these in your matching, because here we're talking about matching, computing maximum probability matching, or no. And once U2 arrives, you can no longer change what you have decided about the previous two edges. And then you have to decide about U2 and so on. So this is an online algorithm, and it's a big area in theoretical computer science, like these kinds of algorithms and how to model them and how to reason about them. And we specifically focused on an algorithm called ranking by Karp and Vazirani, which is a seminal online algorithm, and it was generalized in many ways that are quite important in theoretical computer science. Like, for example, the most notable one is AdWords, which is an online matching algorithm that has been later on used to model online advertisement markets like Google and so forth. And it won, this algorithm won a Test of Time award by the Journal of ACM because of these applications. So it's an important algorithm. What is ranking? You simply have the offline side like this. You randomly permute it. This is the first step of the algorithm. So you get an offline side, you randomly permute it, and then the online side arrives. You randomly permute the offline side so that an adversary cannot change the online side in a way that causes you to mess up the matching that you calculate. So this permutation of the offline side is to guarantee that no adversary can change your worst, like no adversary can really influence your the size of the dimension that you compute. Once every, so as I said, every vertex arrives online. So here, for example, V1 arrived with the two edges from the previous example. The ranking does a very simple thing. It just takes the edge that is connected to the vertex with the highest ranking. So here we take U3 because this is the edge that's connected to the highest ranking. And then here, V2, we take U1 because again, this is the highest free ranking vertex. And then V3, it comes with 3 edges, but we cannot take U1 because U1 is no longer available because it has been matched to V2. So we take U2 and so forth. All right. So I will skip, I'll be a bit faster here. I will try and be a bit faster so that I can finish in 6 minutes or so, hopefully. So the algorithm, from a modeling perspective, it's a bit more, it's different from what theorem proving systems have been traditionally used for. So it has a randomized component and it has an online component. So the probabilistic, it has a probabilistic algorithm, probabilistic component, and an online component. So the probabilistic part is just the part that draws a random permutation of the offline side and permutes it. And the online side is one that monitors every arriving vertex and makes that simple decision that I told you. It just takes the edge that connects it to the highest ranked free vertex. All right. And so the theorem statement for an algorithm like that is a probabilistic one. So what we say is the expectation of what this algorithm returns has to be greater than or equal than 1 minus 1 over e of the maximum possible matching if you know the entire input from the beginning. Because yeah, it's a bit suboptimal, but so what was I saying? So you have a probabilistic statement that you want to prove about this algorithm that is over the expectation of what would happen when you're permuting the offline side. And the proof of this algorithm, this online algorithm, is a non-trivial one. It has been studied. The pen and paper proof, just pen and paper proof, has been studied at least those 5 times. And there's a new paper still by Vijay Vazirani about it. So it's a complicated proof that people have been trying to simplify over a number of times, over a number of iterations. So the goal of the formalization, which I did with Christoph Madlener, one of my students in Munich, former students in Munich, was to formalize a specific proof by Ben Baum and Matteo. And that proof, the paper says online Buckner matching made simple, and they claim that they have provided a simple combinatorial proof for it. So I'll try to make 2 points. The first, or 3 quick points. The first one is that we model random probabilistic computation with GLA monads. We model online computation with just recursion on lists. So the online input is a list of inputs. I won't be able to go into the details of the proof, but the proof has a few parts. The first part is a probabilistic part, and in that part, all what we were doing in the theorem prover were just to prove the equivalence of different distributions, and this when you're doing theorem proving, this means you prove the equivalence of different GLA monads, and other than just getting your head around with representing distributions with GLA monads in a theorem prover, there's nothing challenging about that I can say. Like, we didn't come up with anything mathematically interesting. It's all about just getting your head around how to model distributions as GLA monads. And the second part is the combinatorial part, and that has a critical step in it. And that step is the following. What is the difference between the output of the algorithm if you, how would the output of the algorithm change if you remove one of the vertices? So here in this example, if we remove U2, what would happen to the output of the algorithm? So if you look at the graph, because you know when a vertex arrives, every vertex arrives, you just take the next the uppermost free vertex in the ranking. Or what will happen is that your matching will cascade down. So for example, V3 won't be able to be matched to U2, so it will just take the next one, which is U4. So this blue edge will be instead of the red one, and the same V5 will then not be able to match to U4 because it's no longer available. And then V5, and then V6 won't be able to be matched to anyone. So the difference between the two outputs will be that the matchings cascade down, and if you look at any graphic representation of that, you will be able to immediately see that the difference between the sets of the difference between the two matchings is just an alternating path here. So a path in the old matching, a path in the new matching, a path in the old matching, a path in the new matching, a path in the old matching, and this is the difference. So and indeed they say it's an easy structural observation to see that this is the difference. But when you try and do that in theorem proving, then it becomes in a theorem prover or it becomes a very different problem, because the first thing is, how do you even model this graphical figure that we have there? So this was the vast majority of our effort. Like this was almost 60% of the project, just modeling that difference between the two outputs, which needed to be modeled as a complicated mutually recursive function, and proving properties of that function. And I don't think that this is just about tedium in theorem proving. This actually is more fundamental. Because the challenge that we had was, can you really express what's going on without using any figures, or without describing any figures in natural language? Like I think if you try to come up with a verbal proof, even without a theorem prover, that really avoids describing a figure but tries to just do it in an algebraic way, it will be much harder than just looking at the picture. So yeah, the last category, there's just one slide I want to say here. The last type of results I wanted to discuss is connecting matchings and linear programming. And this is very different. So I showed you a classical algorithm, an online algorithm, and here we're talking about just encoding a problem into another problem. And this is also, this is practically interesting because it can relieve you of the burden of implementing one of these matching algorithms, and instead you can just use an LP solver to solve matching problems. But it also is quite important theoretically, because linear programs have given people completely new perspectives on matchings that led to milestone results. If you look at the matching from a linear programming perspective, you see very different structure. Like you have different insights and different intuitions. And the only thing that we did until now on that was to show that the linear program encoding bipartite matching is integral. What does that mean? So this is a linear program that encodes whether an edge is in the matching or not. But note here that these are real numbers, right? Because this is a linear program. But although the solution space is made of vectors of real numbers, this program cannot have a solution that is not integral. And this is why that result is interesting. I won't be able to go into the proof, of course, but the proof here deals with very different concepts. So we deal with polyhedra and faces of polyhedra and intersections of polyhedra. And yeah, we'll talk to you in details if you want later on. But it's a different type of concepts that you want to model. So I'm now done. I just wanted to say that I talked only about matchings, but Thomas here is working on minimum cost flows, and Maximilian is working on micro-decision processes, and both of them will talk about their work next week. And it's also, all of these areas have equally interesting problems. And there's still much more to do. There's matroids, and this has been barely touched in a theorem prover context. And my own, I just want to say one sentence. So I think that in combinatorial optimization, there are problems that really would benefit from theorem proving. And the most important one of those, in my opinion, that I'm currently working, or not, the most important one that is within reach currently, is the verification of the so-called Mikhaili-Vazirani algorithm for maximum cardinality matching. This is the fastest algorithm to solve the problem. It's 40 years old, and it doesn't have an accepted proof until now. Vazirani has published 3 papers, and every time after they're published, after years of reviewing, there is a mistake, and the status is back to where it was. So this is a fun quote that I took from, I asked him to give me for these talks about finishing that, about how he would see finishing this project, and he thinks it would be cool. I mean, he's exaggerating, of course, but I think it would be cool. Yeah, thank you.